everybody hit the gas law channel for the some the gas law demon? Is that him?
So before we jump into gas laws, we have to talk about specific variables for each one. All right. So the variables. First up, we have P, which stands for pressure. And pressure can be kPa or ATM. Next up, we have V, which is volume, which is in liters. And we have not K, we have T, which is in Kelvin, which is where the K comes from. Kelvin degrees. So the reason we don't use Celsius degrees is because there's negative Celsius degrees. And if you were to do the math later on in the video, you'd realize if you plug in a negative number, you might get negative pressure or negative volume, and that's not possible. So next up, let's talk about the STP, standard temperature and pressure. For pressure, the standard pressure is 101.3 kPa or 1 atm. For temperature, it is 273.15 degrees Kelvin, as it is equal to 0 degrees Celsius. And even though it's not included in the STP name, you also have to take into account volume, which its standard form is 22.4 liters, because that is how many liters make up a mole. And another thing to take into account is the R value. And the R value is more useful for the ideal gas laws, but for kPa it is 8.31 kPa, and it is 0.08206 atm. So these are the variables you want to use when you're going to be dealing with gas laws. And if there's a question asking for the STP, these are the things you want to keep in mind.
Hey, you with the glasses, shut up.
Me?
Yes, you have glasses on, so shut up.
Oh, I do have glasses.
You're removing more lot of that bag.
I have no idea what that is.
You know, P1 times B1 equals P2 times B2.
Never heard of it. So talking P as in plastic or B as in fish?
No, P as in pressure, B as in volume. You know, the adding of pressure to something makes the volume decrease and vice versa.
So like this. My pressure being my hand, which I don't understand how that makes sense. Making this bag smaller is what you're saying.
Yes.
Is that bothering you?
Yes, you're gonna get us killed.
Is there a murderer here?
Yes, there is.
Oh boy. Oh boy. Is that him? First, we're going to be starting up with Boyle's Law. Alright? So Boyle's Law states that pressure 1 times volume 1 is equal to pressure 2 times volume 2. Now what his law states is that pressure and volume are inversely proportional. Alright? This means if one rises, the other one decreases. And let me show you Boyle's action in an example problem. So let's say P1 is 1 atm. And let's make volume 20 liters. And P2, let's make that 5 atm. And volume can be, let's say X, because we're trying to solve for volume here. So to get X by itself, this little dude, you have to divide both sides by 5 atm. So you would cancel out the atm right there, and the 1 times 20 is just 20. So then 20 divided by 5 will give you a grand total of 4 liters being the X value. As you can see, the pressure was 1 to 1 and it turned to 5, which the pressure increased. And volume was 20 liters, but it went to 4. This shows how Boyle's law is inversely proportional. You can use this gas law when temperature has to be at a constant, and you have to be working with problems with pressure and volume.
That's him. That's him. That's him. That's him. That's him. Get him. Stay back. Stay back. Hey, oh, come on. No. Oh. 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 Toxic gas. No. Oh.
I am not afraid of using this. I know Gay-Lussac law, which is P1 over T1 equals P2 over T2. Meaning if I light this up, then it will make the molecules go faster, crashing into each other, making it explode. I warned you.
So next up, we have Gay-Lussac's law. Alright. So this law states that pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. Now, unlike Boyle's law, this gas law is proportional. Whoops, misspelled that. Proportional. Alright? This means if one rises, the other one rises as well. So, let me show you a problem just to let you know what I'm trying to say here. So let's make pressure 1 atm, just keep it simple. And T1, let's make it 300 degrees Kelvin. And we're trying to solve for pressure 2, so that'll be X. And let's make T2 600 degrees Kelvin. So to get X by itself, you have to multiply by 600 to cancel this one out. So then 600 times 1 is just 600, and that is over 300. So 600 over 300, if you think about it, it's really just 2. And 2 is the new pressure, or 2 atm, which is the value for X. Now, Gay-Lussac's law, you want to use this gas law when you're dealing with pressure and temperature. But like Boyle's law, when temperature has to be at a constant, this one, volume has to be at a constant. And that is when you use Gay-Lussac's law.
Okay, according to Charles' law, if I do this right, V1 over T1 equals V2 over T2.
So now we're going to be covering Charles's law, alright? Charles's law, Chucky. Let's call him Chucky, alright? So Chucky's law is volume 1 over temperature 1 is equal to volume 2 over temperature 2. Now you might see that it's very familiar to Gay-Lussac's law. The only difference here is that instead of pressure, we now have volume. And of course, it is proportional. As in one increases, the other one increases as well. And since in Gay-Lussac's law, volume has to be at a constant, in this one, since pressure isn't in the equation, pressure has to be at a constant. So let's just do a practice problem, just a little refresh on how to do these type of problems. So volume 1, let's make that around 200 liters, alright? And temperature 1, let's make that 100. And it's equivalent to volume 2, we're trying to solve for that, so that is X. And let's say it is 300 degrees Kelvin. So you multiply both sides by 300 degrees Kelvin. So that would give you 6,000 over 100, which is just, not 1,000, that's 100. And that would really just give you 60, which is, in liters, because it's volume, it's X, or volume 2. As you saw, the volume 1, which is 20 liters, increased to 60 liters. and while the temperature was 100 degrees Kelvin, rise to 300 degrees Kelvin. This shows how it is proportional and similar to Gay-Lussac's law and the complete opposite of not Charles's law, Boyle's law. And that is Charles's law, and remember, it has to be when pressure is at a constant.
You were dead.
You were wrong. You fool. You could have used the combined gas law or the ideal. She could have used the gas laws, but let's hide the evidence. I was never here.
So in the video you saw that I was mentioning combined and ideal gas laws. So for right now we're gonna stick to the combined gas law, alright? The combined gas law has all the gas laws put together. We have Boyle's, Gay-Lussac's, and Charles. Let me show you what I mean. So P1 times V1. Sound familiar? That's because it is Boyle's law right there. And it is all over T1. Now if you think about it, P1 over T1, that is Gay-Lussac, and volume over T1 is Charles. And this equation has to equal to, obviously, P2 times V2 over T2. So, as you can see, obviously, it is all the combined gas laws. So, let's just do a practice problem to see how you would solve one of these. So, we can make pressure 1 745. That does not look like a 4. 745. We can make volume 1 2 liters, and then over, let's say, 298 degrees. Let's make that equal to 760, and we're trying to solve for volume 2 here, over 273, right? So, we're trying to solve for volume here. So you would do first, you would multiply both sides by 273, right? So then you would have 745 times 2 times 273 over 298 is equal to 760x. Now, to get the x by itself, you have to divide this whole thing by 760. So I recommend you take it in smaller chunks. Solve for this number first, and then solve for the 760. I'll just give you the answer right here, right now. Volume 2 is equal to 1.8 liters. And that is how you would use the combined gas law. So we already talked about the combined gas law, so let's talk about the ideal gas law now. Alright? So, the ideal gas law. It is pressure times volume is equal to moles times the R value times temperature. So, something you want to take into account right off the bat is that pressure and the R value have to be the same variable. Alright? Because you can't go from kPa to ATM. You'll be doing a lot more math there since you have to do 101.3 kPa to go to ATM, and it's a lot more work on yourself, and it'd be easier if you kept the same variables. Alright? So you would use this equation to find any variable. So I'll just get into it right now. So pressure, you can use that by having N times R times T, all of this divided by volume. As the other problems, you try to get P by itself, and since you're multiplying, the opposite of multiplying is dividing, so you divide the other side by volume. And for volume, it's basically the same thing, you know, just instead of dividing by volume, you divide by the pressure. And for temperature, you have to do pressure times volume divided by moles, small n, times R. The reason for this is because you want to get T by itself, so you just get rid of the N and the R. Since you're multiplying them, again, the opposite is dividing, so you divide this by N and R. And the amount of moles, same thing as temperature, but instead of having moles, we would have temperature instead. So that is how you would solve each equation for the ideal gas law. And since we haven't worked with anything with moles yet, let's do our practice problem involving moles. So, trying to solve for moles here, alright? So, let's make the pressure, normal pressure 101.3. And let's have the volume 5 liters. Temperature, let's make that 200 degrees Kelvin. And the R value, since we're sticking to kPa, gotta use that 8.31. So, you want to do here is you just want to multiply the top out, multiply the bottom out, and do the math. So, I'll just whip out my handy dandy calculator here. So, 101.3 times 5 is equivalent to 506.5. And that is divided by 200 times 8.31, which is a whopping 1662. So you would just divide, solve for n, and that would give n being 506.5 divided by 1662 being 0.3047 or 0.305 moles. And that is the ideal gas law in action. Again, it is to solve any sort of variable that you need to find. And you can use it to find a specific variable for a gas law. Say they give you the amount of moles, temperature, and the volume. But you need to incorporate Boyle's law because it's pressure and volume, but you don't have the pressure value. So you use the ideal gas law to help solve for that value. Hope you enjoyed it. Subscribe.